Hi and welcome to this video series on NMR spectroscopy. I'll be your course instructor. My name is Gokul and I'll be taking you through NMR spectroscopy as per the MSc Part 2 syllabi of the University of Mumbai. Let's look at the broad overview of the syllabi, and the syllabi has NMR split over two units. One of them is termed as Advanced Spectroscopic Techniques 1 and the other one is called Advanced Spectroscopic Techniques 2. And the unit begins with proton NMR, starting with some basic recapitulation, followed by chemical magnetic equivalence, and then followed by first order, second order spectrum. So what we'll be focusing on in this first video will be recap of various terminologies involved in NMR spectroscopy, and also a brief overview of what exactly is an NMR spectrum, when do we get an NMR spectrum, what are the criteria to be met by a nuclei to exhibit a positive NMR absorption. Okay, so let's get started, and before we get started with any spectroscopic technique, one thing that is fundamental for us to remember is that spectroscopy is just a branch of science that deals with interaction of electromagnetic radiation with matter, and that is fundamental to all spectroscopic techniques. And the electromagnetic radiation which is under consideration in NMR spectroscopy is the radio frequency radiations, and the energy levels that it targets are the nuclear spin states. So there is transition from one spin state to the other. These spin states become available to a certain nuclei that is NMR active, with a finite difference in energy between them in the presence of an applied external magnetic field. So all this comes about based on possessing a fundamental quantum property of a certain nuclei called as a nuclear spin, and the nuclear spin is designated as I. So where we are at is the property called as nuclear spin designated as I, and this nuclear spin is quantized in the sense that it can't take all the continuous values possible. There is some quantization in which it can take only certain discrete values, and the discrete values that are possible for nuclear spin are ranging from plus I to minus I. But it can't go continuously between plus I and minus I. It'll have to go in quantum increments of 1, 2, 3, 4, and so on. So the total number of values that a certain nuclei can possess for the spin then becomes 2i plus 1, and these many spin states become available to a certain nuclei to hold in one of the quantum states that is possible. As is clear from this table number 3.1, that the total number of spin states is dependent on the nuclear spin quantum number, and this nuclear spin quantum number can hold values of either 0, which you can see right here, or it can take half integral values like these 1 by 2, 5 by 2, 3 by 2, etc., or it can take integral values like these for deuterium and for nitrogen. So when is it that a certain nuclei takes 0 spin or a half integral spin or a complete integral spin depends upon the nucleons that is present in its nuclei. And if we had to establish a qualitative relationship between the atomic number, the mass number, and the value of I, it would come to somewhat like this. Say for example, we have an odd atomic number for the nucleus and an odd mass number, then the spin quantum number for that particular nucleus is half integral. A most characteristic example is that of hydrogen. It has an odd atomic number as well as odd mass number, and the nuclear spin quantum number has turned out to be half. Okay, compare the same thing with C13 here. think we should be comparing it with F19 and with P31 here. Here also you have an odd atomic number and an odd mass number, and likewise for P31 as well, we have an odd atomic number and odd mass number. In each of these cases, the total net nuclear spin quantum number takes up values of half integral. Okay. The other possibility is that you could have an even atomic number and an odd mass number, and still the spin state that you would get would be half integral. Now here the example happens to be of C13, wherein you have an even atomic number, that's 6, whereas the mass number is odd, that is 13, and you have the total spin quantum number of the nuclei turning out to be 1/2. Same thing applies to oxygen here. It has an even atomic number, odd mass number, and the total nuclear spin happens to be half integral. Okay, the other possibilities are that the atomic number is odd but the mass number is even. In these cases you get an integral spin, and the most characteristic example here happens to be of deuterium and of nitrogen. So you have an odd atomic number, 1, 7 respectively for hydrogen and nitrogen here, but you have even mass numbers. For deuterium you have the mass number as 2, and for nitrogen the mass number is 14 here, and both of them turn out to have an integral value of nuclear spin. The last possibility is having even atomic number as well as an even mass number. In these cases the nuclear spin turns out to be 0. Okay, so here we've examples of C12 and O16. All these nuclei happen to be NMR inactive. So for NMR active nuclei, the criteria has to be that I should be non-zero. Could either be half integral spin or it could possess a complete integral spin, just that the total spin of the nucleus should not be 0. The last two things to be discussed about the spin states is that the total number of spin states or total number of energy levels that are available to transition between in a nucleus happens to be 2i plus 1. So those many spin states are available for transition to take place based on absorption of some characteristic energy from the electromagnetic radiation spectrum. However, all these nuclear spin states happen to be completely degenerate. That means they are energetically equivalent so long as there is no external magnetic field that is applied. Because each nucleus with some characteristic spin quantum number happens to be oriented randomly in three-dimensional space, and these random orientations of all the many nuclei that are a part of that particular molecule will cancel each other out, and there'll be no net spin that will be exhibited by that particular substance. However, in the presence of an external magnetic field, these tiny bar magnets starts aligning themselves with respect to the orientation of the applied magnetic field, and thereby then there will be multiple spin states that will become available, and the total number of spin states will then be governed by this 2n plus I 2i plus 1 rule. So this brings us to the discussion of how is there an absorption of energy to transition from the ground state to an excited state, and what are the phenomena involved. What we've already looked at is that when we have say for example the external magnetic field that is applied, and we see the energy difference that is created between multiple spin states as a function of the external magnetic field, you see that as the strength of the external magnetic field goes on increasing, the difference between the energies of the spin states goes on increasing, and ultimately the frequency of light that is absorbed so as to go from the ground state to excited state also goes on shifting to higher and higher frequencies. Right? Now that having been established, what we will be looking at now will be the theoretical basis for absorption of energy. And based on this graph, it's clear that the difference between the energies of the ground state and the excited state happens to be a function of the external magnetic field P naught. Now this can also be given as being equal to h nu. If at all we talk about light of frequency nu being incident on the molecule so that it can flip from its lower spin state to a higher spin state. Now since both are energy units, they can be equated, and equating them gets us to an equation that would look somewhat like this. And the introduction of this symbol here, gamma, happens to be what is called as the gyromagnetic ratio. And this gyromagnetic ratio happens to be a very, very characteristic property of every nuclei. Some of the gyromagnetic ratio of nuclei have been given in this particular table, wherein it says that the H1 isotope happens to have a frequency of about 42.6 when a field strength of 1 Tesla is applied, and the magnetogyric ratio is also given in radians per Tesla. So you could either express it in frequency units, or you could express it in radians per Tesla, and you see that it's got a very, very high value, and that's indicative of the fact that when you incident a proton with some finite external magnetic field, it results in a large separation between the states, the ground state and the excited state. Compare that to the next heavily probed nuclei in organic chemistry, that's the C13 nucleus. And in the C13 nucleus, you see that the gyromagnetic ratio happens to be just a fraction of that of the proton. It's about 67.28 in units of radians per Tesla, and it's about 10.7 if at all you look at it in the frequency units of megahertz. If we go through a little bit of math, we'll see that the F over here can be replaced with h over 2 pi, because that's how angular frequencies and angular momentums work out. And if at all we equate it with the energy associated with the electromagnetic radiation that is incident on the nuclei to transition from the ground state to the excited state, we get this relationship, which when equated gives us the relationship between frequency of the electromagnetic radiation to the gyromagnetic ratio and the applied magnetic field. And if we substitute experimental values here for a proton, typically we get that when the external magnetic field is exactly 1 Tesla, putting all the values in place, we get the value of frequency to be 42.6 megahertz. That's exactly what has been specified here as well. So that's the gyromagnetic ratio. A few terms will keep repeating through all the standard texts which are there involving NMR spectroscopy. One of them is precision, and the precision happens with a characteristic frequency called as the Larmor frequency. And this is fundamental to understanding how absorption of electromagnetic radiation takes place, and also answering another fundamental question, that why is it called resonance? And both these questions will get answered when we look at the way a nucleus behaves in the presence of an external magnetic field. So when an external magnetic field is applied, not only does the nuclear spin get established, but apart from it undergoing a spin motion, it also performs something called as a precession, like that of a spinning top under the influence of gravitational force. Now this precession happens with a characteristic frequency, and this frequency of precession is called as the Larmor frequency over here. Now, when the external electromagnetic radiation h nu is applied to this nuclei such that the frequency of electromagnetic radiation matches with that of the Larmor frequency, there is a characteristic absorption of electromagnetic radiation which takes place. Okay, so having understood how absorption of electromagnetic radiation takes place between various spin states that become available in a nuclei, the presence of an external magnetic field, we're coming to the last part of this particular video, wherein we'll be discussing about the excess nuclei that are present in the ground state, because only when there are finite number of nuclei in the ground state can we take them up to an excited state. And if there aren't enough nuclei in the ground state, you would reach a state in a spectroscopic term that is called as saturation. And when there is saturation in the peak that should have otherwise looked like this would then become blank, because that particular peak is going to disappear as the energy states are completely saturated. There is no more room for more number of nuclei to go to the excited state from the ground state. So this excess nuclei concept is something that follows from our normal Boltzmann distribution, and the normal Boltzmann distribution of n upper upon n lower can be given by e to the power minus delta E over kt, where k is the Boltzmann's constant. If we do a little bit of math to this particular equation, whereby we substitute delta E with h nu, because h nu will be the frequency of light that is incident on the nuclei to transition from the ground state to excited state. And if at all we substitute mu for 60 megahertz, and we are looking at what should be the difference between the energies of the ground state and excited state for a proton when 60 megahertz is the frequency of light that is incident on it, then we get an n upper upon n lower value that comes to 0.999991. That means only about 9 nuclei are in excess in the ground state as compared to that of the excited state, and this population is called as the excess population or the excess nuclei in the ground state. And we see that there is a relationship between the frequency of light that is incident on the sample and the number of excess nuclei, and that's why resolution becomes better as you go to higher and higher field strengths, because you will not probably be touching the saturation limit, due to which the peak heights would often become smaller and smaller, especially when you're operating at lower frequencies with respect to the NMR. So when you are at 60 megahertz, you have only about 9 nuclei, which is in excess. But as you go to 200 megahertz, you have about 32. And at 600 megahertz, you have about 96. And hence the resolution would keep becoming better, better, and better. To sum up what we've discussed in this video is that we've introduced NMR. We've talked about a concept of nuclear spin I. And we've discussed the criteria for a certain nuclei to be NMR active. And to get you to recapitulate that, all nuclei must have non-zero nuclear spin so as to exhibit a positive NMR signal. Then we discussed some concepts about absorption of electromagnetic radiation so as to give an NMR signal. We also discussed concepts of precision and Larmor frequency, and we discussed the criteria for absorption, which also happens to be a resonance criteria, and that's probably the reason why we have the term nuclear magnetic resonance associated with this spectroscopy technique. Finally, we came across excess nuclei and saturation as a concept that helps in resolution of the spectrum. What's coming up next will be the chemical shifts, and we'll also be discussing different types of NMR spectrometers. See you in the next video.